Okay, so for the last two questions of 7.1, number 3 here, two astronauts are going to use their jetpacks to maneuver apart for the space station into position. The first astronaut applies a force of 750 newtons horizontally, while the second astronaut applies a force of 800 newtons vertically relative to Earth. Wait a second here, doesn't this look familiar to you guys? Determine the resultant force on the part. So this is the same. Um, this is the same, where am I here? This is the same as video 6.4. So in video 6.4, we were using geometric vectors, and now we're going to be learning this using Cartesian vectors. So the benefit, obviously there would be a benefit, or else why would we show you, is we can actually kind of avoid drawing, right, when we're doing Cartesian vectors. And also you saw here, scale doesn't matter. The drawings don't need to be as particular, because also I don't even need to have a drawing to do these questions. So just to show you how it was drawn out in 6.4. We had our compass directions here, the north, south, west, east. And when I read it here, the first astronaut applies a force of 750 newtons horizontally. I think that was usually orange. So I have my 750 newtons horizontally. Again, I don't need to put a scale. Let's say like that, because I know 800 has to be longer. So I'm just looking that I don't want to go up too high. And then the second astronaut applies a force of 800 newtons vertically. So then I'm coming up from here, and I just have to make sure it's a bit longer, which that looks longer to me, and write in that this is 800 newtons and that this is 750 newtons. So if I were to place, right, the origin right here would be the coordinate point of 0, 0. Should change my color, I guess, to black. Then the coordinate point here would be along the x-axis 750, and vertically I'm not moving, 0. And along here would be, again, the x-axis would be 0, and I'm moving vertically up 800. So my resultant vector, if I'm going to be determine the resultant force, so to figure out the resultant vector, I'm going to be adding these two vectors together, right, to get the resultant force. So just to go back, just stay with me here to go back in your notes in terms of adding vectors right here. So if I have vector u, which let's say is the orange one, and vector v, which is the green one, vector u plus vector v is just adding u1 and v1, your x's together, and then adding u2 and v2, your y's together. So that's what we're going to be doing, is adding our x's together and adding our y's together. So I guess I'll put that in red, since that's usually the resultant vector in red. So the resultant vector is my horizontal component, again, of adding my, well, let's just say the two vectors that I'm adding together first. So I'm adding the vector 750 horizontal and vertical together with the horizontal and vertical components of the other vector would be 0 and 800. So now when I add them together, it would be 750 plus 0, my x's, and then 0 plus 800. So the components of the resultant vector would be 750 horizontally to the right, and then 800 up. Okay? So I have the components of my resultant vector, but if it's asking me to determine the resultant force, then I need the magnitude, and then I'll eventually need the direction, right? So to get the magnitude, let's put it over here. To find the magnitude, right, absolute value of the resultant vector is adding my x's together and adding my y's together, right? But I already added my x's together, I already added my y's together, so I can just go right to the component parts of the resultant vector. So that would be 750 squared plus 800 squared. So large numbers here. I have 562,500 for 750 squared, and 800 squared is 640,000. So putting those together is 1,202,500. And that would be 1,096.6 newtons, which if you were to go back to video 6.4 or your notes from 6.4 is the same. I mean, it should be, right? We're in trouble if it's not. Lesson I'll put, because it doesn't have to be that you go to the video, you can just go to your notes that you took, right? Okay, so there's the magnitude of our resultant vector. So now to get the angle, right? Again, I don't need, just to kind of show you though, I don't need to be drawing anything, but just to show you where we're at here. So I have my resultant vector that was going 750 units to the right, and then it would have gone 800 units up. So it just has to be more up than out. So let's just say something like this. And we just found out that the magnitude of that is 1,096.6 newtons. And again, this horizontally is going to the right 750. And this vertically, we were going up 800 there. So the angle that we want is, again, from the x-axis up, counterclockwise, is that theta there. So to find our angle, we have, if I was standing there, that's the hypotenuse, that's 90 degrees because horizontal and vertical. So this number would be 800, this number would be 750. We have this number here as well, but again, we want to probably go with the numbers that they gave us. So let's go with opposite and adjacent. So therefore we would use tan of theta equals opposite first over adjacent. It doesn't always have to be that the large number's on the bottom, right? So again, then angle theta would be equal to the tan inverse because I'm getting an angle of 800 divided by 750. So you could have taken 800 divided by 750, get that value, and then take the inverse tan of that. Or if you can do it all in one step in your calculator, I have angle theta being a value of 46.8 degrees. Okay, so therefore it's asking for the resultant force on the part. So therefore the resultant force on the part is, therefore the resultant force on the part is our magnitude of 1,096.6 newtons at 46.8 degrees. And again, we could have said from the horizontal, but what would be better is to say above, because we are at the horizontal, we are moving above. So that's more specific, above the horizontal. Okay, and there's number 3. So to finish off here with question 4, this one should also look familiar, just as a hint, from the same section, 6.4, same video, same lesson. A cruise ship's captain sets the ship's velocity to be 26 knots at a heading of, again, that 0 is kind of a dead giveaway that it's a true bearing of 80 degrees from the north, moving clockwise. The current of the water is flowing toward, right, a bearing of 153 degrees, and it's moving at a speed of 8 knots. What is the ground velocity of the cruise ship? So again, what is the ground velocity? Means to get the resultant. Let's write that down. What is the ground velocity? Find the resultant. And again, we've already done this question. We know what the answers are. We're trying to figure out maybe an easier way to do it now using Cartesian vectors, and where we don't have to really do the drawings, which would help for sure, because that took up a lot of time in 6.4, right? So in order to get the resultant, I'm going to be adding 2 vectors. So again, we already looked at that formula for number 3, adding the 2 vectors, adding our x's and adding our y's. So if we were to go back to the 6.4 lesson or the video, like your notes, the resultant vector was just below the x-axis. Okay, just to kind of keep that in mind. We'll come back to that at the very end of the question. So to just to kind of get our bearings, well, I guess there is a pun intended there. Let's draw the ship's direction. So the ship's velocity is 26 knots at a heading of 80 degrees. So again, that would be drawing a vector that's going north, right? Clockwise is the true bearing, and 80 degrees would be somewhere around here. And we'll draw in that from the north in this direction is 80 degrees, and that the magnitude is 26 knots there. And then if that's 80 degrees, then this would be 10 degrees, right? And this is the ship. Then let's draw the current. And then we don't have to have these drawings anymore. It's just to kind of establish and compare between the two right now of how to start up using a Cartesian vector based on where we left off of from 6.4. So here the current is flowing toward a bearing of 153 degrees. So to draw that in, again, north, 90, 180 is too far. So I have to do 90 plus 63, right? So this is 63 degrees past this x-axis south. So it's more than 45 degrees. I'm not really at the origin there because it doesn't really matter with the drawings. I'm just going to say like that. And I would draw that in as a magnitude of 8 knots. And our direction here is 150 degrees from north for a true bearing. But again, the angle that I want to use, right, is from the x-axis counterclockwise. So here I have my 10 degrees. So I need to figure out, I should probably do that one, sure, in red. I don't have red. So again, this one here is 10 degrees. The angle that I want to use, the angle that I want to use here is, again, starting at the x-axis and going counterclockwise all the way around to there. I got to figure out what that angle is. So our angle is going to be 90 plus 90, or if you want to just write down 180 plus another 90, or if you want to just write 270 plus what? What are my degrees here? I said that to draw 153 was 90, and then 153 minus 90, this chunk here, I'm trying to just do dots, this chunk here was 63 degrees. So then if I took 90 minus 63 to get the leftover part, so plus 90 minus 63, which 73, 83 is 27. So then 90 plus 90 plus 90, 270 plus 27 is 200. If you want to double check, 297 degrees is the angle that we need to use. So let's write this down in terms of our component parts. So this side here would be equal to the magnitude that we have, 26, right? And it's always cos first for the horizontal of our angle, which would be 10. And then 26 of sine, 10 degrees. And for this side here, that's one vector. For other vector, right? And then we're going to add the two of them up. Would be, again, what is our magnitude is 8 by the cos of our angle, 297, and then the vertical component would be 8 of sine, 297. Okay, so we have to add those two Cartesian vectors together to get our resultant vector. So our resultant vector is simply taking our x values, 26 cos of 10 plus 8 cos of 297, comma, adding our y values together. 26 sine of 10, just be careful, plus 8 sine of 297. Based on how tired you might be, depending on where you are in the course and how many hours you've put in today, stop and go back and look. Am I doing x with x, comma, am I doing y with y, right? And just to state here, I'm adding, just change my color here, adding my x components together. That's all I'm doing. I'm just going to put COMP, adding my x components together. That's what I'm doing there. And then here, I'm just adding my y components together. Okay. So our resultant vector is going to be, you might be able to put all that into your calculator, but again, be careful, maybe try just that and adding them together, and then double check that if you do the whole thing that you get the same result. So you know if your calculator can do that or not. You should get a positive value of 29.2, and then adding these two components together, you should get negative 2.6. So again, I'm moving to the right from the origin, 29.2, and I'm moving down 2.6. I don't know if I said that at the beginning of 4 here, but if we go back to 6.4, I think I did. The resultant vector is just below the x-axis. So if you think about moving horizontally 29.2 and down only 2.6, that makes sense that it's just below the x-axis. So far things are making sense, right? So now to find the magnitude, I have the components of my vector. I don't have the ground velocity. I don't have the resultant. I don't have the magnitude of it, and I don't have the direction of it. So to find magnitude, of this vector, right? Absolute value of vector r of my resultant vector, the magnitude, is to add my x's together and to add my y's together. So I'm just going to stop here and have you guys think about this. My resultant vector that I have, right, I said was from the origin moving out to the right 29.2 units and down 2.6. So it's starting at the origin. So it's a position vector. So if it's a position vector, to add my, subtract my x's would be 29.2 minus nothing. And to subtract my y's would be negative 2.6 minus nothing. When I have a position vector, I can just go right to using these values themselves. So 29.2 squared plus negative 2.6 squared. So that is equal to, did I write down both of them? 29.2, I have 852.64, and that negative times a negative is positive 6.76, which adds up to 859.4, 859.4, and the square root of that is 29, roughly 29.3. So that's my magnitude. So go up, and that's measured in knots. 29.3 knots is my length, basically my magnitude of the resultant, right? So now to find the direction, I think I can squeeze it if you guys will just not mind my messiness here, over here on this side. And from what you've told me, your writing is smaller than mine, so you can probably fit it here or maybe even below the, right, obviously down below. I just don't want to erase this. So for the direction, now here I want to just draw something for you just for an understanding. Quick, we're almost there. Again, what I was saying was for my resultant vector, it was moving 29.2 units horizontally and then just down 2.6. So just to kind of, again, I'm going to go a little bit more than it would make sense, but just to state here, I'm moving to the right, right? 29.2 units, and I'm moving down 2.6. Because it's down, I don't need to put negative, okay? The negative is telling me what direction to go in down, but the length of that vector, let's say, would be 2.6 to think of it that way. So because I'm horizontal and vertical, that would be 90 degrees there. And I'm trying to figure out this theta here. that angle in there, right? So again, I have numbers 29.2 and I have a number 2.6. I also have 29.3 knots, but like we said, we should use the numbers. Well, technically none of these numbers are given to us, but I guess for lack of me writing out the third number, let's just do opposite over adjacent and do tan. So I'll change back to dark green. So then tan of theta would be opposite 2.6 on top over 29.2. So then angle theta would be equal to the tan inverse of 2.6 over 29.2. You guys go ahead. You should have 5.1 degrees, yes? And that should be the same as the previous video. So for our therefore statement, oh, I'm sorry, I'm just going to try to squeeze this in. Now again, for our therefore statement, we're giving our magnitude. So we have our magnitude. But in terms of the direction, all of the directions in the question were from true bearing. So I'm going to answer this as true bearing. Okay, so true bearing would be starting from the north. Just work with me here. I'm going 90 degrees, right? Plus below. I'm going 90 degrees plus that 5.1. So I'm just going to add it in as 95.1 true bearing in my therefore statement. So therefore, the ground, because it talks about ground velocity, it doesn't exactly say resultant. So I'll say the ground velocity. Just write this down below, neater than me. Work with me here. The ground velocity, I'm just going to put, so this is part of the tan answer here. The ground velocity in brackets, we are getting the resultant. The ground velocity or resultant is roughly 29.3 knots is our magnitude at, what's our direction going to be? Remember, true bearing has to have 3 digits, so 0, 95.1 degrees. And then because we know that's true bearing, we don't have to give any direction. We know we're starting north and going clockwise, and that would be the resultant vector there.